We're going to be looking at computational methods. Now, you've already come across the term computational thinking, and that will be things such as, pattern matching, and in the OCR GCE, be looking at things such as thinking logically, thinking abstractly, and so on and so forth. Now, these are kind of strategies we use when we're going about solving problems. So we'll think abstractly about the problems and make sure we focus on the most important parts. We'll think procedurally so we can break it down into modules, etc, etc. Computational methods, on the other hand, are strategies that we use to solve problems, but these are kind of like characterized and categorized. So, for example, you might have a problem such as solving Sudoku, where backtracking would be the best solution for it. So these are tried and tested methods which can be employed to solve certain types of problems. So for a certain type of problem, we'll have a computational method which will fit in with it. Sometimes we might be able to use multiple computational methods. Sometimes none of them will be appropriate. It depends on the problem. So we are going to be looking at what they are and how to apply them to different problem contexts. So this is the area of study that it comes under, computational methods, and there's quite a lot in there. What I'm going to be focusing in on. So today's lesson, we're going to be looking at if a problem is deterministic or not, and I'll explain what I mean by that in a moment. Decomposition. Which we have already been introduced to in the course, but I've kind of like clarified why it's a computational method. And then we're going to be looking at some key methods such as backtracking, data mining, heuristics, performance modeling, pipelining, visualization. So let's get into it because there's a lot of detail to cover. Now, first of all, we need to understand what we mean by decidability. Now, this on its own isn't necessarily on the specification, so you don't need to be able to categorize whether a problem can be solved using computational methods or not. However, it does link into the coursework nicely. Okay, so in order to solve a problem, so given any problem that you can think of using algorithm, we need to make sure that that problem is decidable. So that basically means whether we can actually write an algorithm for it or not. If we can't write an algorithm for it, or this algorithm will just never finish because of whatever reason, then it's not decidable. We can't write a program to solve it. And there are some problems which would come under this kind of bubble of undecidable. So a decidable problem is one where, given an algorithm that we could write, it will stop after a finite time. Now, the word finite doesn't mean 10 seconds, it could mean a couple of years. Okay, as long as the algorithm at some point will stop, then that problem is decidable. Doesn't necessarily mean that that solution is good. Okay, so that is a completely separate area of study, if I'm honest with you. Very much related, but very, very different as well. So for any input, we'll arrive an output. Okay, so given an input, we'll get an output. And there must be a function, an algorithm, which will translate that input to output. So the last two are fairly obvious because I have an algorithm, it takes the input, it gives me output. Okay, you can imagine any algorithm doing exactly the same thing. The first one is the most important part, is that we will eventually stop a given answer. An undecidable problem is one where there's no algorithm that we can create. Okay, no matter what we do, how good we are, or what language we use, or anything along those lines, it just cannot be done. So how does this link into coursework and the course? Well, basically, when you are creating your coursework and you are in the analysis phase and you're trying to decide what features you are going to implement, each one of those features must be decidable, and part of the mark scheme is all about showing that you can that is computable, that you can actually create an algorithm. It is decidable. You must be able to design an algorithm to solve it, because otherwise you won't be able to code it. Now, it sounds like a really hard job to be able to show that something is decidable or not. Actually, it turns out to be really easy, and this is where your existing application research comes into it. So you will have already researched existing applications for your coursework. If another application can do it, then there must be an algorithm that exists that you can maybe simulate. That's a very simplistic view of it, but essentially, if existing apps do the feature, then you should be able to do it as well within reason. Okay, so if you've got something like being able to predict the best stocks to pick on a given day, it might be there's an application that can do it and maybe even have some success with it. Doesn't necessarily mean you will have the skill to develop it. So there's always that little caveat as well. But on the simplistic view of it, if another application can do it, you can do it too. So let's now really get into computational methods. So the first one I would consider to be computational thinking rather than a method. So it's basically an approach we can use to solve any problem. Okay, so that's why it's different to a method. So imagine a situation where I want to create a mobile app for a school. Okay, now that app might have different features. Okay, so it might have a timetable function where you can see your timetable and it'll tell you what lesson you should be going to. Homework section where you'll be able to see and do your homework, maybe a news feed, having whatever's happening in the school on that day, and maybe a school calendar to see what's coming up in the future. So we can easily break our school mobile app into those 4 key sections. So that is decomposition, where we break down our problem into smaller parts. Each of those problems might then be further broken down, and then I can get into a situation where I can maybe start to design functions for these, or classes and objects for them, etc, etc. So first of all, I want you to just have a little think before we go on in the video. How could you maybe break those individual parts into further parts? How can you subdivide this problem even further? So here's an example of how you might do it. Now, genuinely, there's no hard and fast rules for this. This is all about how you would think about the problem in order to maybe decompose it. As long as you decompose it as far as it can go, then it probably will work the way it should do. And in real life, in real software development teams, they would decompose it, but they'll probably discuss it at the same time. So the designer will discuss how they're going to break it down. They'll have a discussion about it to get the best one. Okay, so there will be some disagreements, obviously, because that's what happens. But obviously, eventually, the kind of hive mind mentality will hopefully get to the solution. So here's some examples. The timetable, well, I obviously want to make sure you can log on to the security checks. You can't access your timetable without logging in. Maybe gather data from SIMS, which is a school database, which has all of the kind of information about your timetables and everything else, in fact. And then our ability to be able to view the timetable. Okay, you might even have other features in there, such as highlighting the current lesson you're supposed to be at, maybe a little note saying you're late, you're in the wrong position, whatever happens to be. So you know, you can use your imagination to actually add more features should you wish to. So object-oriented design principles go nicely with decomposition because we can start to think about these kind of subdivided parts as classes. And then those classes will obviously have attributes and methods, and then you can start to think about, well, how are they all going to link together? For example, you notice in my previous decomposition I had login a few times. Well, the login system could maybe be a class. And in that class, it might have the logon feature. We'll check with the logins, things like that, and other classes can then use it, and objects can use it in order to check whether someone's logged in or not. Okay, so that's kind of an object-oriented view of the world. So when we start to look at object-oriented programming, you'll start to see how decomposition and OO design kind of go hand in hand. So again, this really links into coursework exceptionally well because first of all, this does come up in the exam as well, by the way, so you might be asked to decompose, but genuinely they're dead easy questions. They're much more likely to ask you why do we decompose, but again, it's not a hard question, so nothing to worry too much about it. In the coursework, however, it's actually quite tricky because the decomposition itself is dead easy. You know, I haven't met a student yet that really massively struggles with it because it's kind of common sense, isn't it, if you think about it? But being able to justify why you're doing it, that is much more tricky, and that is where the marks for decomposition come from. Basically being able to say, okay, I've broken down into XYZ modules. This is the reason why I've done it. It's the justification. So you must make sure you link back to your previous knowledge of reusable components, thinking procedurally, why do we kind of use functions and procedures and all that kind of stuff, and also linking back to your OO. So actually at this stage, this might be a tricky ask because you haven't got maybe all of the theory yet, but you will eventually in order to be able to do that, certainly very soon. Now, we're going to be having a little activity before we move into the first computational method, which is backtracking. Okay, so in order to kind of get an idea of what it is, you're going to play a game. Okay, I'm sure you're gutted about that. The problem is called 8 queens, and first of all, I'm going to say have a go at it first. Okay, don't cheat because obviously the answers are on the internet. You could cheat. Don't try it. I want you to figure out, well, if you do manage to solve it, what method did you use? Okay, it's not necessarily that there's an algorithm directly that you can use to solve it, but there's this thing called backtracking which can be used to solve it. So the link is in my YouTube description as well as in my OneNote for those using that. And the problem is quite simple. You're trying to place 8 queens on a chessboard. Okay, the queens cannot take one another. So remember, queen can take vertically and horizontally and also diagonally. So you can't place another queen on the same row or column or on the same diagonal. It sounds easy, but it's actually really, really hard, and it will take you a little while. The link is, as said, on the board. There are other websites which have 8 queens. If you want to Google it, that's absolutely fine. I don't mind. So, how does this link into backtracking? So, backtracking works on a premise called partial correctness or partial candidate solutions. That's a really posh way of saying it's kind of like a solution. You're kind of halfway there. Okay, give you a clear example. Imagine you're playing the 8 queens game and you've placed 3 queens correctly. Okay, that is considered a partially correct solution because you managed to do some of it but not all of it. Okay, so it works on this premise of partial correctness. So in order for backtracking to work, you need to be able to very quickly create partial solutions, partial candidate solutions, and do it incrementally. So I can build on them. So I place 1 queen, then 2, then 3, then 4, and so forth. We can very, very, very quickly check to see whether it's correct. So in the 8 queens solution, which I'll go on to in a second, it's trivial to basically check to see if there's any queens going up, down, left, right in the position we just tried to put it in. And also, we need to be able to abandon a move. Okay, so the last move we've made to undo it in sense and have another go. So for example, let's say I placed 7 queens and the 8th one won't place. Maybe I undo one move and try that move again. Okay, and that undoing is what's known as backtracking. Okay, so let's see it in action. So imagine I've got my 8 queens board and I place 1 queen. Okay, this is a partial solution. Now it's a trivial one because I've got 1 in there. It's fairly noddy, but it's there. We also, to go alongside this, we have a stack. Now, those you may not remember stacks or maybe not studied it yet, I don't know, you should have by now. A stack is essentially a data structure where the last item being added to the stack is the first being taken off, effectively like a stack of books. So you take always off the top of the stack. So we use a stack to keep track of our moves as well. So I've placed 1 queen on the board, so I've placed 1 item in my stack. Okay, and this is just a coordinate. Okay, so 0, 0. So you can imagine, maybe I'll just get a black pen. That's column 0, row 0. I don't know why I wrote 1 there. There you go. Column 0. So partial solution should be easy to check following the rules or not. So whether it's following the rules or not. So in the 8 queens one, it's dead easy to check whether a queen's been placed. So we just simply go up, down, left, right, diagonally. Is it there? Is there another queen in that row or not? Okay, and we can do that as we place a queen. Okay, so we don't have to place all the queens and check every single queen. We just simply check the last queen that's placed. So how could we do that? And here's a bit of a chance for you. So here's a kind of a partially written algorithm to actually check to see whether a queen has been placed correctly or not. Okay, this is our check. So remember, as part of backtracking, being able to quickly check whether a solution is correct or not should be really easy to do. And here's an example of how it's easy to do. So I'm passing through as parameters the x and y coordinates of the queen that I want to place. I then will check vertically, horizontally, and diagonally. So I've written the code for vertically already, okay, whilst I'm going to get you guys to write the code for horizontally and diagonally as well. So how does it work? Well, first of all, I iterate over each of the rows. Okay, so starting at 0, go all the way to 7. It keeps the x coordinate the same because I'm always looking at the same column. Okay, so imagine I'm placing it here, for example. Then it goes through, and if any of these are a queen, so going down here, if any one of these queens, in fact, you can see obviously the first one is, then it won't place, it will return false. So as soon as it sees another queen in a column, well, it can't work because obviously queens can take vertically at any distance, therefore it returns false. If it goes through all three checks, because the horizontally and diagonally work very similar, then it will simply return true, saying yes, it can be placed. So there is a link in my description to some code for you to actually play online. You can try it online. It contains code display boards and other kind of helper code as well. And I'm going to explain the code in the next slide. So this is the code that I would like you to change. Now I've already created some of this already to help you out. So if I run the program straight off the bat, you can see it is currently displaying an 8 queens board. Okay, it's all text-based to make the code a bit simpler and a bit shorter. As you can see, I have got kind of grid references here. So I've got X and Y, and I've placed 2 queens already. And you can see there's a third queen here that's not being placed. So let's actually go into the code. Now this first line of code is just simply creating a blank board with nothing in it. That's just so we've got an initial 2D array to work with. Then we have got the code that you are going to be changing. So the check queen function. What this function will do is it'll take in a coordinate x and y. It will then check the board to see if there's any queens either vertically, horizontally, or diagonally to basically make sure that the rules are being met. I have used board as a global. I'm fully aware that I could probably pass it through as a parameter, but I'm just a bit lazy. So there you go. Here I've got the code which will check vertically. Now, vertically obviously is going up and down. And you probably notice I've got the I variable in the first position, and then I've got X as the second one, which is, it sounds back to front, doesn't it? But actually this is just how the 2D array has been created, because if you think about it, I'm creating a row, and a 2D array is an array of arrays. So the first array is the first row, the second array is the second row, and so on and so forth. So if I'm thinking about going vertically up and down, actually I'm looking at the first item in the first array, the first item in the second array, the third item in the third array. So we're talking about which array is it going in, ergo it's going to be the first one. So when we do a 2D array like this, it is just back to front, which is a bit weird, but there you go. The draw board code is simply just going through the array, and if it sees an empty square, it's print out space. If it sees a Q, it'll print out a Q. I could probably make this a lot quicker, but this is just the way I've done it. I'm also printing out the numbers, just so it looks a little bit neater. I'm sure I can make this look even better, but again, I'm just going for quickness. Then I've got a very simple function called place queen, and what this will do is it will make use of the check queen function, and that returns either true or false. True if it can be placed, false if it can't be placed. If the queen can be placed, it will actually place it, and again notice that the y and x is back to front just to make it work. Otherwise it will print out a little error message as the one you can see here. The other thing you can change in this code, should you wish to, is which queen's been placed. So I would like you to first of all write the code to check horizontally and diagonally, and then make more placements, place more queens. So you can create more function calls of place queen just to see if you can actually place them, and then finally solve the 8 queens problem. Okay, so just create a solution using this code as you can. Notice I have got a draw board function there, which is simply going to draw the board at the end. If you want to, you can maybe turn this interactive and you can have a little loop going. However, that is not necessarily necessary for this task. So now we've kind of worked out how we can quickly check to see if whether a solution is correct or not at a given point when I place a queen. We can now continue on with backtracking. So imagine I start to place more queens. So I'll put a second queen in there. You can see I've added it to my stack. So it's there. I made the move there, and there's my queen there. Let's move on to the. So I then place all my other queens. So now I've got to a point where I've placed a number of queens. However, this last queen that I try and place isn't going to work because if you can see, there's a diagonal here. Now, as it turns out, no matter where I place that queen in this column, it's going to not work because if I place it here, bang, that's not going to work because it will take that way. If I place it here, well, no good. Place it here. No good because of that one, and you get the idea. You can probably see that it won't work in any one. So we've got a problem. We cannot proceed. We cannot place the last queen. Therefore, we need to backtrack. So what we do is we start undoing moves. Okay, so that means pop in the stack. So we're going to undo maybe this move and maybe the next one, and then we try again. So we don't undo the entire lot. We don't get rid of it all. We simply undo 1 or 2 moves, try again. If that doesn't work, we'll undo a few more moves, try again, and we go through that process. So sometimes we might have to undo multiple moves. So in this case, what I've done is I've undo 2 moves because the other one didn't work and I've kind of skipped ahead a little bit. And then I've placed another queen here, okay? And then I'm going to try that one. So, well, if it's there, will it work any better? Well, if I maybe put it here, does that help? No, it doesn't because obviously it will take there. So maybe I have to undo a few more moves and so on and so forth. So when backtracking, we pop the move stack. We pop the stack that's keeping track of the last move that we have made. And then we try again. If that doesn't work, we undo again, try again. And we just go through that process until we find the solution that does fully work. So to summarize all of that, because there's quite a lot of detail there, backtracking can be used when we have partially correct solution, where we have a solution that can be said, well, this is kind of right, this is kind of right, this is kind of right, and now it's fully right. Okay, so that works very well for things like Sudoku, obviously the 8 queens problems, and there are others as well that will work in one, and you will have a chance to research that in a moment. We need to be able to test the correctness really quickly because if it takes ages to check correctness, then the algorithm's going to perform incredibly poorly. If there is a problem where we can undo previous additions and to try a different path, to try a different strategy, then it will work for backtracking. And we will use a stack, and that is really important. Remembering it uses a stack to keep track of those moves. Okay, that's a really, really important bit of information. This keeps going until we've reached a solution or we've exhausted every single possibility. This approach is better, more efficient than brute force, because brute force will just try every single possible move. It might get lucky or it might be the last one it tries. Backtracking is a refined way of doing brute force because it's trying out solutions, and when it's find one that's kind of works, well, it sticks with it until it proves that that partial solution doesn't work anymore, or it finds another one. So it's commonly used for puzzles, so it's very common in puzzles, but it's common in other things as well. It's also used in something called declarative programming, which mercifully has been taken off the A-level specification. It's something you'll come across in university, and some people like it. I did not like it, I'll be honest with you. So you'll have some tasks now in OneNote to go on to, some questions. I've actually copied these questions into the YouTube comments as well for those people watching YouTube video only to have a go at it as well, because it makes sense to practice what you have just learned. The next computational method to look at is called data mining. Now, data mining is something where people get a little bit confused because they think data mining means SQL. Okay, so remember, part of the course is looking at databases. So we look at normalization, we look at SQL, and you'll be forgiven to think that data mining is simply really big SQL statements going into a database and pulling data out and doing something with it. That is not what it's about. So it's got nothing to do with SQL per se. Okay, SQL is needed because we need to be able to talk to the database in order to pull data out. But data mining is about finding trends and patterns in data rather than actually just doing a simple select statement. Okay, so select statements are not data mining. So companies will have vast amounts of information stored about you as an individual. Okay, and we do mean generally vast amounts of information. This data will have been collected about the customers and individuals for a long amount of time, for a vast number of years. Ergo, we're talking about huge amounts of data. Now, it's advantageous for companies to try and find patterns in that data. For example, let's say we have Sainsbury's and they want to know when's the best time to discount, I don't know, frozen pizza, for example. Okay, they want to know that so they can sell more pizza and they can make more profits. It might be that if they discount pizza, then people are going to pay more money for beer, for example. I don't know. It's common for data mining to bring together lots of disparate data sets, so lots of different data sets, to see if we can maybe pull information out of it that we wouldn't necessarily have seen before. So there's a lot of data mining techniques you can use. The vast majority of them are way out of the scope of A-level because they are complicated, to say the least. However, the principle behind it, the idea of looking for patterns and trends, is a fairly straightforward one to understand. So let's look at some examples of how this might be used. So service providers, so people who provide a service to you, so utility people, mobile phone companies, will have a probability score associated with each customer, and this is the probability they are going to leave. Now, those people with a high probability will have offers targeted at them. Now, this makes you might think this is a bit weird. I'll give you an example. Let's say you were near the end of your contract on your mobile phone and you wanted to try and get a sweet deal out of Vodafone or whoever it is. And you ring them up and say, okay, I'm going to leave you guys if you don't give me a good deal. And they might say, oh, fine, that's fine. That's enough. I'm sorry to lose you. Good luck to your next provider. And you probably go, well, why aren't they not offering you lots of good deals? And it might be that you've been with them for 20 years and you've never changed, and you're ringing them up all of a sudden saying that you're going to leave them. The likelihood is you're not, that you're a bit of hot air and you're not actually going to leave. You've got a low probability of leaving. On the other hand, if you've been making lots of noise about leaving and it looks like you are likely to move around, and you also a high value customer, so you spend a lot of money with them, they are much more likely to target you with discounts and offers and things like that to try and keep you. And they're going to use data such as the interactions you've had with them, your billing information, even what websites you've gone to. So let's say you're on their website and you are just looking at loads of phones on their website. Well, if you're spending loads of time on their website, it's very likely you're going to stay with them, isn't it? So they can use all that data, and they actually generally will give every user a score, something along those lines. Second example is a bit more of a weird one, and this is one that I found on the internet. I do not know how true this is, but you can actually see where it's coming from. So what they've done is they analysed data from supermarkets, and they found they can accurately predict if a customer was pregnant by the contents of their shopping cart over a period of time. So, for example, if someone is pregnant, and even if they don't know it yet, they're going to be more sensitive to sights and smells and things like that. So they are more likely to start buying unscented. If they definitely know that they are pregnant, they are going to be avoiding certain things, and also they're going to be starting to buy certain items as well. So certain vitamins, certain things. I won't go into any more detail on that. So as it turns out, they could use this data so accurately they can not only work out whether someone is pregnant or not, but also their due date, which is quite scary. And that way they can start targeting adverts to them, give them discounts and vouchers, try and get them back to the shop for things like nappies and dummies and all those kind of things that a family would need when they're having a new child. So this is just another example. Other examples might include, I remember I read a news story about this where a kind of a supermarket in America used to have nappies right at the front of the store, right next to beer. And they found that actually that was a really, really good combination, because what was happening is, families were running out of nappies late at night, and they would send the bloke out saying, "Go and get some nappies." Then the bloke would go in, grab the nappies, go, "You know what? I fancy beer." So you get some beer as well at the same time, rushes to the counter and rushes home. So just a silly example, but this is generally what's happening in supermarkets. They will try and identify what you are most likely to buy and what would entice you into their store in order to buy more stuff with them. They want you to spend money with them, and they spend a lot of time analyzing data and predicting your purchasing habits in order to sell more products. So to summarize, data mining extracts trends from large sets of data. It can be used to analyze current trends and help predict future ones, and that future prediction is very, very, very powerful for companies and something that they will want to use a lot. They can be used to find trends that weren't maybe previously known before. So there's not much point trying to analyze and predict a trend that you already know about. You want to try and predict trends that you didn't know about, so you can then exploit it for profit. Other areas that this might be in, so for example, fraud prevention. So for example, you can analyze and predict your spending over a year, and if that spending suddenly changes for no real good reason, that might be a sign of fraud on your account. So they can then block your account, ring you up saying, "Did you buy this thing from Russia?" or whatever happens to be. Obviously, target sales I've already talked about, and customer support and retention I've already talked about as well. These are just examples, by the way. There's millions of other examples you can actually look at. Now, as I said, the actual mechanics, the techniques used to actually do data mining are very complex. However, there's a method called K-clustering, which is simple-ish enough for you hopefully to understand. So it's just really, you do not need to learn this for the A-level at all. However, it's just a way of kind of experimenting with data mining. It's the only one I could find where you could actually have a little bit of programming chance to it. So I've included the link to this code I'm about to show you on the internet as well, on YouTube and OneNote, and you can have a go at the following. So if you comment line 18 and uncomment line 21 on the codes when you see it, you should see a scatter chart. And the scatter chart will look like this. So this is an example of data mining where we're basically trying to predict trends in a bunch of data. So the data we are going to use is here, and it's essentially showing the eruptions, how long an eruption lasts for, and how long it waits until the next eruption. Okay, so there's a lot of data here, as you can see. There's absolutely tons of it. You'll be able to kind of run this code and try it out inside Trinket. You don't need to install all the libraries because it will take you a little while. Anyway, so this code, there's not much to change. So when you run it initially, what's going to happen is it's just going to show you a bit of the data, and it's just going to show you in a bit more of a nice format. If you comment out line 18, like so, that's going to hide it. And then if you uncomment out line 21 and run that again, what you'll see then is a little scatter plot of all the data. So as you can see from the human eye, there seems to be some groupings there. So they're kind of all clustered around 2 points. We can then use data mining techniques to actually try and identify those clusters. So I'm just going to uncomment this last bit of code, line 53, and I'm going to comment out line 21 again, so we just see one of them, and I run it again. And what we should see is, you can see it's now kind of colored the two groups together, and it's kind of put a point where it thinks the two clusters are at the center of them. So this was all done through a statistical method rather than actually me saying where those points were. So that is what data mining is. It's looking at data and trying to find a pattern and a trend, in this case two clusters. Then if you uncomment line 21, you uncomment slide 53, you should then see the same scatter chart, but this time categorized with central points put into the thing. So that categorization was done automatically using this thing called K clustering. So it essentially predicted which ones should be in which group. So it was done thing. So you can then think about, well, what information can I pull from that? What trends has it spotted? Okay, and that was done automatically using the K clustering technique rather than actually done by human. So we've gone through quite a lot so far. Now's a good time to maybe pause after the task you've just done to actually make some notes. So backtracking notes. What is backtracking? What do we mean by partial solution? And explain using examples how backtracking can be used. When you are explaining backtracking, make sure you talk about stacks. That is absolutely crucial. And this idea of undoing moves. So pop in the stack and try another move out. Data mining, talk about what we mean by the term big data, purely because that term might pop up in the exam. What do we use data mining for? This idea of predicting trends and patterns in vast amounts of data, and why would a company want to use it? So give some examples that you may be finding on the internet, or maybe some of the ones I've already discussed in this video. You also might want to do some extended reading on all this. So I've got 2 links here for you to try out. So these are some techniques that you can use to do a data mining. So those who are interested in how to predict trends and patterns in a set of data, do have a look through this. Okay, and again, I will include this in my YouTube comments as well as my OneNote. The video from Suraj explains how it works and how to implement it. Suraj is bonkers. I love Suraj. His videos are crazy. He's a crazy person, but he's crazy clever as well. You know, so his videos on machine learning, all kind of data science related stuff are really accessible, and he just does tons of stuff. He's an absolute machine. His stuff is amazing, so do check him out. Now the next one we're going to be looking at is heuristics. Now we will come back to heuristics in another unit when we start talking about pathfinding and A*. So that's where we kind of look at a practical use of heuristics. However, we're just coming across the idea now. So this is another method of solving problems. Now, some problems can be solved. However, the solution just takes a long time to do. And that solution, when it takes too long to do, means that we can't realistically use it in the real world because it just would take too long. Sometimes it might also be where you know, we can't get a perfect solution. So for example, for those who use voice assistants or maybe like Alexa or something like that, it doesn't always get it right, does it? Sometimes it thinks you say something really random. That is another heuristic. So it's doing its best attempt at understanding what you say and what you mean. However, it won't always perfectly get it right. So that is another example of a heuristic. So this is where we find an approximate solution rather than a perfect one. So it's not going to be, in the example for Alexa, a perfect voice recognition system, but it's good enough to be able to use it on a day-to-day basis without having to really pull your hair out and actually get stressed over it. You can see, obviously, Alexa's really caused me stress over the years. That is a joke, by the way. Approximations tend to be faster to commute. So if we had a better one that would just take ages to work out, then it wouldn't work as a consumer product, because you can imagine saying, Alexa, play me Queen music or something like that, and it would just take 10 minutes before it plays the music. That is not useful. I've just triggered my Alexa. That is brilliant. Alexa, cancel. I don't know if you picked that up on the video. I might actually leave that in because it's quite amusing. So be very careful when you say the A word in a house with Alexa in. Anyway, some problems are so computationally hard that finding approximation is the best solution. It's the only way we can actually do it. So let's move on. Sometimes algorithms can work as a best fit. So we find kind of an approximate solution or best fit solution rather than a real perfect solution. So for a heuristic approach to work to solve a problem, we need the following criteria. So is the difference between the heuristic and the perfect solution close enough? We don't want a situation where, let's come back to voice assistant as an example, where we say something to the voice assistant and it just doesn't understand us at all. Okay, it must understand us enough, maybe 90% of the time it gets it right, for it to be usable. If it was only working at 10%, then we wouldn't be able to use it. Therefore, the heuristic model that we're using would not be suitable. If the execution time of a heuristic approach is smaller than the accurate solution, so am I saving time by doing it as a heuristic? So if the perfect solution maybe takes 10 seconds to do and the heuristic takes 9 seconds to do, then well, I might as well just do the perfect solution. What's the point of doing the heuristic version? So heuristics are used in very niche situations where the computational time to a perfect solution just takes too long, or just can't get to a perfect solution, and we're better off with a best fit, like an example of voice recognition or face recognition. Now, one classic problem which is really hard to solve and takes a long time is a traveling salesman. Now, this problem is very straightforward. So what is the best route for a salesman to visit every single node on this graph and arrive back at the starting point? Okay, so what route can they take? Maybe going from A to C to J, then going this way. What routes can they take which will be the shortest route but allows you to visit every single node and return back to the start? Now, have a look at this graph. You might think, well, okay, I can work this one out for myself. As it turns out, when the graph gets big enough and we have enough links on it, this becomes an incredibly hard problem to do. And the only solution that will guarantee the best route is actually try every single possible route. About that. As I said, you can have a go at maybe finding the most efficient route. It's a nice little task to see whether you can do it yourself. But the travel salesman problem is a problem which no one's found a way of perfectly solving it in the brute force way. So if we have 5 cities, then the amount of time it takes, and this is just a number, by the way, it's not seconds, anything like that, it's just a number. This is based on its complexity theory. So if you've not studied complexity theory yet, this is essentially the rate of growth of the algorithm. So as the number of cities increases, the amount of time it takes will also increase. So as I said, these are just numbers to help show the growth. So with 10 cities, you can see the number has astronomically increased. When we get to 15, that number's gone crazy. By the time we get to 50 cities, well, that number is absolutely bonkers. Now, the traveling salesman problem is one which is actually a real problem. So, for example, delivery drivers, what's their job? They have to go to lots of different places and arrive back at the depot. That's a traveling salesman, isn't it? It's exactly a traveling salesman. And they're going to have more than 20 stops in one day. You know, it's going to mean that they have to use a heuristic. So the heuristic approach to this, as you can see, is much more manageable. So when we get to 50 cities, the difference between the brute force, the kind of perfect solution, to the heuristic one is astronomically massive. Okay, so trying to run this with 50 cities on a real computer just wouldn't work because it would just take too long, whilst the heuristic approach does. So how does this heuristic method compare? Well, on average, the paths are 25% longer. So it's not optimal, but for large number of cities, the only practical solution that we have. Okay, so how the solution works for the heuristic, if you are interested, just Google it, you'll find it. It's a little complicated, but I'm sure you guys are clever and can work it out. To summarize, heuristic algorithms are approximate solutions. So they're not perfect solutions, they are approximations. They are best fit. They're used when the perfect solution would be too computational or difficult to work out, it will take too long, or we just can't actually get a perfect solution, for example, like voice recognition. Heuristic approximations are much quicker than the ideal solution, so they should be able to run in a reasonable amount of time, and that time be a lot shorter than the actual perfect solution. And sometimes heuristic approximation may be too far off the perfect solution, and in this case a heuristic should not be used. So if we have a situation where the heuristic gives me a 10% success rate, well then it's not necessarily going to be practical to use that in real life. So here's a task. Again, I'll put this into my YouTube description. Why do you think virus scanners employ heuristics? Okay, so why they use a heuristic approach to detect new viruses? So there is an article to read about this, and also if you want to, there are some other examples of heuristics on the second link on here. I will put both of them in my YouTube description. Just to say, the 101computing.net for A-level students and GCSE is a phenomenal resource. The guy who makes these is an absolute legend. Do go onto it. He has absolutely got some amazing interactive stuff on there for a variety of things. So I do encourage you greatly to have a go at it. So here's a chance for you to make some notes as well, so a good time to pause. Explain what a heuristic is, explain why heuristic may be needed, and what is this trade-off between the perfect solution and the heuristic. Okay, give 3 examples of where heuristics are used and explain why a heuristic is needed. So for example, why we need it for voice recognition, why do we need it for face recognition, why do we need it for the traveling salesman, and what's the trade-off, what are we losing by using the heuristic. So the next one is performance modeling. So there's not a huge amount to say about this one, in all honesty. It's not one of these things that comes up a lot in the exam, but let's just kind of quickly go through it. So this is about monitoring systems with the aim of improving performance and efficiency. So essentially it's given any system, how well is it doing. So I'll give you an example. Imagine London Underground. Okay, so London Underground, there's lots of trains going through there, there's lots of people going through there. How can we maximize the efficiency of the trains, of the getting passengers through to where they need to go to? That will be an example of performance modeling, where we'll model the performance, we'll create a simulation of it, and we'll work out, well, if I change this, what would happen? What would be the best way to use our limited resources for it? So any system where I can measure performance in some way, so maybe on a computer network or London Underground or a road system or air traffic control, anywhere where I can have a kind of way of measuring performance, it can be used. And can I then use performance modeling to improve the situation? Can I simulate it? Okay, simulations and performance modeling go hand in hand. So I must be able to simulate it in order to performance model it. So again, if I can create a simulation like an air traffic simulation or a train simulation or a road simulation or anything where I can simulate it, then bang, I can use performance modeling. And also it might be anywhere there's a queue. So how can I model a queue being used? For example, a print queue. Or a scheduling and operating system. Okay, and again that could be simulated. Again, that idea of a simulation comes into it, and then I can try different ideas out to see how that impacts the simulation, and ergo does it improve performance. I will be going over pipelining in a separate video as well, mainly because there's two aspects of pipelining you need to be aware of. One is pipelining as a general principle, what is pipelining, and secondly, how it links in with the CPU. I purposely put this in a separate video purely because people get this really confused. Whenever they hear the word pipelining, they immediately think of the FDE cycle, which isn't necessarily wrong, but it's bigger than that. There are other situations which use pipelining, and it's important to actually go through that in detail. Okay, so that's a separate video that will be coming up at some point in the future. The last one is visualization. Again, there's not a huge amount to say about this. The Legend 101 Computing has got a brilliant page on this with lots of examples of visualization. I generally can't explain it any better than they have. It's got lots of examples of where visualization has been used. Just go on that website, have a little look through that website. That's all you need to know about it. It's simply the idea of, okay, here is something, some form of data, and can I pictorially represent it on the computer? That is all it is. It's really, really dead easy. Okay, so can I take data and visualize it, and what are the different ways I can visualize that data? Okay, it literally is what it says on the tin. So to summarize visualization, visualization method of showing ideas in a visual form. It can be used to map abstract ideas such as computer networks, for example. They can be both static or animated. They don't tend to be programmed. They tend to be programmed and not just drawn, hand drawn, because I mean that's just someone drawing something, then, isn't it? So it's not a visualization. So 101 Computer has got some good examples, and this link here, again, I'll include this in the description. It's got some more examples as well, and I think this topic is best learned by just looking at lots of examples. Make some notes on those last two methods, ladies and gentlemen. Make sure you explain what they are, give some examples of them, and again, there's not much to write about those two, so don't spend hours and hours making detailed notes on it, because it's not a big part of the spec. Okay, so we're almost done. Here's some further reading if you are interested in some of these topics. This is purely just to help you understand it in a bit more greater detail. These links will be in the description, as I've already mentioned. So yeah, do have a look through some of these. It's always good to take a topic and read into it further and research further, because it'll help you understand the basics better. Thank you very much.